So today we are pleased to listen to a talk given by Professor Joseph Francos, who is currently a professor at Ben Gurion University at the Department of Electrical Computer and Computer Engineering. He also heads the Mathematical Imaging Group and the Signal Processing Track. So his current research includes parametric modeling and the estimation of multidimensional signals, image registration, estimation of object deformation from images, manifold learning, parametric modeling, and estimation of 2D random fields. So now I let the talk to Mr. Mohamed Najim, who is going to say a few words about Professor.
So good afternoon. So I'm very happy to say some few words about this old friend. I happen to say old because he's very young, but this friend. I know Yossi for a long time. Yossi is graduated from the best institution in Israel, the Technion, and he works with Boaz Porat. He's also a guy everyone of us know now. And when he got his position, he started to be really one of the leading people in the multidimensional signal processing, image processing, pushing a lot of maths in this area. So we interact very early. And as far as I remember, I think I visited him early in the 90s, and he picked up me in the Gaza border at the time. And also he used to visit us, probably I think the first time it was 1997, during a workshop organized with Professor Kailat and Patrick Lewitt from the Deaf University in San Antonio, and then you came back for the PhD as a member of the PhD examination board of one of our PhD students in 2000, and also he came back on 2005 during the IEEE SSP, and at this time we have so many bright people like him and also like Kaiman and so many others. So I'm very happy, and on behalf of all of you and myself, I mean to thank him. He is here in Bordeaux and France as in a private visit for tourism, and I want to thank him because we got this slot of time so we can interact with him, and after that he had to pick up his family. Thank you for coming, and thank you for the talk.
Thank you for inviting me, and thank you for it's quite a different situation than what we used to be in for the last 2 years. So it feels like a little bit back to normal, conditional back to normal. So what I would like to speak about today is detection and tracking and recognition. Well, in my view, they are all intermixed of deformable objects using structured dimensionality reduction. This talk, I'll try to, when I build this talk, it is kind of what I had in mind is kind of giving an introductory talk to the whole concept. If we have the time, I'll jump to some briefly to some new presentations. Two of them presented at the last ICCV. It was about a month ago, again by Zoom, and another presentation which is going to take place in next week in BMCV in the British Machine Vision Conference, again by Zoom. But I'll try to give you some flavors of the new stuff as well. So. What is the idea? The idea is to provide a new framework for detection and recognition of deformable objects, where the idea is that the basic physical idea is that when you observe an object, it will never appear the same way. It will always be, there will always be a geometric deformation and probably some radiometric deformation because illumination changes. And as a result of the action of the family of possible deformations, the set of different realizations, different possible observations on each object is generally a manifold in the space of observations. Now, for those of you that are familiar with group theory, essentially we will formalize the problem as having an object undergoing a group action, and the manifold of observations is nothing but the orbit of possible appearances of the object under the group action. So the key point, the key idea is that images, or if you talk about 3D LiDAR scans, they have huge dimensions in terms of the data, but if you are after the deformation, that the parameters of the deformation that makes the difference between every two observations, if you take the simplest example where you have a rigid object, there are only a rigid transformation is no more than 6 parameters, 3 for the angles and 3 for the translation. And nevertheless, the problem is still complicated, although there are only 6 parameters to be estimated. And this is what is frustrating. Much younger, so much data, and the problem is relatively simple, and we still don't know how to solve it properly. So this is a picture of how the orbit looks like. Essentially, you have this Mona Lisa. Every image is differently deformed observation, and when we talk about the orbit or the manifold of possible observations, essentially each appearance is a point here on the manifold, and the manifold essentially encapsulates the set of all possible observations one may have on an object. In this case, the Mona Lisa. I'll show you other examples later on. Now, the recognition and detection problems, of course, are strongly related. Recognition and detection problems of deformable objects are strongly related to manifold learning and dimensionality reduction. However, in nonlinear manifold learning, methods aim to find the unifying structure of all the observations through a detailed, practically sampling of the orbit, and then attempting to, in a sense, linearly approximate what is in the middle between observations. So essentially, the idea is to densely sample and by densely sampling the manifold to be able to characterize it. Now, what if on the one hand, let me retrace. On the one hand, existing non-linear dimensionality reduction methods don't make any assumptions, and therefore they are more general. However, in practice, when you consider real problems, you know more or less what is the deformation the object undergoes. For example, you don't know the exact deformation, but you know the family of possible observations, especially if you think about, again, the simplest example of a rigid object, it can either rotate or move, and that's about it. And if you are imaging it, and then you you have the scaling effect, and if you further generalize it, you have the action of the projection group. So in principle, the number of parameters that control most of the observations is relatively small. So the idea here is, well, why, if we have this prior knowledge, let's try and use it. And this is how it works. So we will assume that the geometric transformation belong to some finite dimensional family. And what we will show in what we call the universal manifold embedding, that there exists a set of nonlinear operators that universally map each of the different manifolds, where each manifold is generated by the set of all possible observations on a given object. And this mapping is from the orbit of the object into a single linear subspace that essentially represents this single object under all possible transformations that we consider. And graphically, the idea looks like that. You have the orbit of these three objects, and using the operator, which I will show you next, how we construct it, each manifold, which is a highly nonlinear structure, is mapped into a single linear subspace of Euclidean space, of some high dimensional Euclidean space. And once you have done that, essentially all the tools we all love and know from linear estimation theory come into practice. So that's the simplest form. However, in general, as I have already said, you engage with a problem which is not geometry only, but also there is the problem of radiometric changes. So if we take the simplest example of where you have an affine transformation of coordinate and a monotonic transformation of the radiometry, namely that if you have, consider a passport photo and for G, and G is your template of the object, and G can undergo an affine geometric transformation of the coordinates, and the intensities may undergo a monotonic transformation, which we denote by U. And what we will show is that there exists a pair of maps, which we call R and T, and the linear space H, such that the set of all possible observations on an object is mapped by the radiometry invariant universal manifold embedding into a distinct linear subspace, which is invariant with respect to both the geometric and radiometric transformations. And the idea is that we apply to each observation first the operator R that makes it invariant to monotonic amplitude transformation, but is designed so it is geometry covariant with the affine transformation, and then we apply the universal manifold operator T to map the geometry only problem. We first reduce the problem where we have both radiometry and geometry variations into a geometry only problem, and then we solve the geometry problem and come back to the original problem. So this is how it looks like schematically, where if we had the problem of geometry only, the manifold was very thin and elegant because there were only, at each point, each point represented only a single realization, where when you have radiometric changes, then it becomes more like a spaghetti, because to each geometric deformation, there might be an infinite set of possible radiometric deformations. So let me skip that one. But okay, so once we will be able to show that we can translate the original highly nonlinear problem into a problem of distinguishing between subspaces, our lives become much easier. And the details are as follows. So let me first present the radiometry invariant operator, and then I will explain how we apply, how we measure distances between objects. Okay, so let's go to the simple example where the observation H is essentially, any observation H is a result of applying a geometric transformation, an affine geometric transformation on the coordinates of a template G and some non-linear radiometric deformations. And the idea of how to remove the effect of the monotonic radiometric deformation while being covariant with the geometric transformation is to define this operator, which is, if this operator R, which is essentially, if you think about it more carefully, it is nearly like histogram equalization. So if you want to imagine what's going on here, send them both to some system that does histogram equalization, and now they are equalized. The histograms are equalized. When you write it in terms of in more rigorous mathematical terms, the observation is mapped. You essentially create from the original observation a new observation with its radiometry normalized according essentially to the cumulative distribution of the intensities in that image. And it can be shown that if H and G are related by this transformation, then after applying this histogram equalization to both H and G, then essentially what is left is only the geometric transformation. And then the question, here is the explanation for how do we translate the problem from a highly nonlinear problem into a linear one. So this is a simple, this is a simplification of the idea, but it's very straightforward. So now we assume that H and G are related only by an affine geometric transformation, so that now we define change of variables where y is ax plus c, and therefore x is a to the minus y plus b, and we put everything into a matrix form and rewrite the problem in homogeneous coordinates. These are all technicalities that do not really matter. And now what we do is, here is the trick. We know that H and G are related by this relation. Now apply when you apply a nonlinear operator to both sides of the equality remains as long as you apply the same nonlinear operator. Now, so this is what we have here. We apply some operator WL to both sides of the equality, and we evaluate the zero, and here in what I've written here, the first order moment of the result. And if you evaluate the first order moment of the results, and you simply replace xk by its representation from here, where xk is the case element in x, and you do this simple change of variables and the determinant of the Jacobian of the transformation goes out because it's an affine transformation and it is a constant, what you get is that you have, at the end of the day, you have a linear relation between the observation and the template, and the relation, and it is linear in the unknown parameters of the affine transformation. So if you now repeat this trick and apply a series of nonlinear operator instead of a single one, then and when you write it in a matrix form, you have that T of G is related to T of H through this linear system of equations. And now, since D is an invertible matrix because it represents the parameters of the affine transformation it's a group, it's invertible, then if these two, if TG and TH are related by this equation, then it means that and the transformation, again, I repeat, transformation is invertible. It means that their subspaces are identical, which brings us back to the illustration that I showed earlier. It means that every point on the manifold of the same object, every observation, which means every point on the manifold of the same object, it means that every observation on the same object is mapped by this radiometry universal manifold embedding into a single linear subspace. So the subspaces that are generated from different observations on the same object are identical. This is what is written here, and this bar simply hides it. So the idea is that if you are now in the problem of detection, recognition, tracking, you get an observation on an object, you apply this transformation, and let's take the recognition problem. And so recognition means here that you get library of objects and an observation, and for each of your objects you evaluated its corresponding subspace. Now you get an observation, all you have to do is to measure the distance between subspaces. So, as you probably know, this is not a new problem. Essentially, I will try to talk about it a little bit later. Essentially, it boils down to evaluating a metric on the Grassmann manifold. With the Grassmann manifold is the manifold of all linear subspaces. Dimension M or DM is the Grassmann manifold of subspaces of dimensionality D embedded in of rank D embedded in some higher dimensional space M, Euclidean space. Okay, so how do you easily measure the distance between subspaces? You use the extrinsic measure on the Grassmann manifold, which is practically nothing but calculating, if you have a subspace, calculate the projection matrix on that subspace, and if two objects come from the same orbit, we said that if they come from the same orbit, their subspaces should be identical, which means the projection matrices should be the same. So if you evaluate the Frobenius norm between the projection matrices that result from each of the observation, if there is no noise if life is nice and easy, then you should be getting 0. This is called the extrinsic distance on the Grassmann manifold. And essentially, the extrinsic distance is the L2 norm of the principal, of the vector of the principal angles between subspaces. So essentially, think about it as follows. If you have this two different objects, then the subspaces will be different, and the sum of the sines squared will be greater than 0 if it is the same, if you are observing the same object under different geometric and radiometric deformations, you still should be getting 0 distance between the subspaces. Okay, now all of that was nice and easy in a sense that we derived the entire theoretical approach in the world where every object is isolated from the background, and you know exactly if you are given an image, you know that this example that I mentioned of where G is a reference observation or a passport image of the object, then in this game, all the transformations are geometric and radiometric transformations of that object, and you don't have to separate it from any background. Or if you consider a 3D scan, you have a 3D scan of the object, but the object is isolated from the background. It in the clutter of what's going around it, but just the car itself. So now the second question, if you want to make it into some kind of a reality, is how do you apply it when you don't have a priori the segmentation of the object from the background? And the idea, at least in the imaging, in the 2D imaging applications, I'll show you, if time allows, I'll show you what we do with the point clouds, but the idea is that even you don't a priori know how the surface you are going to picture looks like, and you don't know what exactly the geometric transformation is, and you don't know what the radiometric transformation is. But still, almost any surface can be well approximated by tessellating it into tiles such that any two observations on the same tile can be approximately related by a simultaneous affine transformation of coordinates and a monotonic mapping of the intensities. In other words, locally, even if the surface is highly complicated, you can always piecewise linearly approximate what is going on with any function if you make your approximation fine enough. So this is roughly the same idea. Any surface, regardless of how complicated it is, can be locally approximated by tessellating it into tiles. And this is what the graphics people are doing for a long time. You know, all of you have seen The Lion King, etc. So the graphics there is nearly perfect, and it is all being done by tessellations. So the fundamental idea is the following. You'd like to derive a local version of what I've just described in the following way. You apply some point matching algorithm in order to find tentatively corresponding scene points, and this point matching algorithm can be old style or DNN style, as long as you get your key points. Now, given two sets of tentatively corresponding key points, the idea is that if indeed you take a set of key points, and the problem with finding key points is that usually the rate of false alarms or the number of outliers in the computer vision jargon is enormous. So the idea is that if 2 points indeed match, and if you do it a tessellation around where these points participate in the tessellation, if the correspondence, if these 2 points do indeed correspond, then the entire area defined by the tessellation should match as well. So I'll show you the idea, the implementation of this idea in a second. Here, look, what we did here, we had 2 images of the Grand Canyon taken at different times and different angles. It's called wide baseline stereo in the vision jargon, but the bottom line is that you indeed get 2 observations which have parts of them in common. Other parts are different in each of the frames. They differ by the angle from which you have taken the images, so perspective is different and radiometry is different. So I'll use this example in order to explain what's going on here. So the idea is the following: we apply the key point finding key point matching algorithms, say SIFT again, or any of the currently available DNNs, and we obtain a set of putative matches. Now we take one of the images and we tessellate it. We take this one, for example. We take, sorry, here we took that one. We took this image and we tessellate, and using the key points that were found, we tessellated it into these triangles. Now the bottom line in the idea, I'll try to find here. Okay, here this can be easily tracked. So here you have an assumption that this point matches this point, and this point matches this point, and this point matches this point. Now, if these 3 points are indeed matches, then the triangle that they define should match the triangle defined by the other in the other image. So the idea is the following: you take the set of key points, you tessellate it. Now, your object, the G and H in the previous presentation, in the previous part of the presentation, are this triangle and this triangle. So you evaluate the T of G and T of H, and you evaluate the distance between the subspaces that they generate. Now, if the distance is close enough to 0, you color it with green, meaning, okay, this is probably a match. If the distance between the 2 subspaces is higher than a threshold, you color it with red, meaning there's no way that these 3 points indeed match these 3 points. Okay? So by doing this exercise at various resolutions, and in our case, we require that every point will be colored in green, at least for 2 to 3 resolutions, meaning we use three different tessellations until we declare a point as a match. And what you obtain at the end of the day is that where you see that every green point here, we get essentially dense matching, where each point colored, for each point colored here in green, we know it's a corresponding point in the other image. And you see that although the overlap is only around 1/3 or less than 1/3 of the image, and you see that the dense matching works relatively well. Here are some additional examples. Again, images taken from the internet. We don't have a clue who took the pictures, what were the conditions. And the idea is, again, solve the problem of doing dense matching between this image and that image. And this is the result obtained. All the pictures, all the pixels that were colored here are pixels for which we know exactly what is the transformation that relates them between the two images. Now, this is a quick detection example, quick detection and tracking example, where here the idea is that nobody allows you to learn anything. Someone has marked a region and your problem is to track this region, okay? So this is how it goes. So the idea is that, again, for each, how the tracking is done, for each observation, you evaluate its, you first tessellate it into triangles, you problem to the one I solved for the general case. Let me trace back here. So again, the entire area here is tessellated into triangles. For each triangle, we find, for the points in each triangle, we find their matches in the second image here, and we follow, okay? So it is a local, kind of a local adaptation of the previous idea, where again, since the shape of the object is a priori unknown and can be anything, you apply this, you find your key points, and after you've tessellated the area between the key points, you keep only those triangles where the subspaces that correspond to the triangles have in the radiometry invariant universal manifold embedding space, they have 0 distance. And this is how it looks like. And so the idea is that essentially, as I said, by tessellating an image of an object where you a priori have no idea how it is going to look like and what the radiometry is going to look like, if you tessellate it into triangles such that the geometric transformation is relatively affine and the radiometry is relatively monotonic, which is what happens in practice when you divide it, when you split when you approximate a nonlinear function by a piecewise linear approximation, then you can test for each of these triangles for whether these areas, not points, these areas indeed match one the other. So you increase, essentially, instead of talking about point matching by such a solution, you increase the dimensionality in solving the problem by asking yourself, or by answering the question of whether the entire area match and not just a single point. And it is the advantage is that it is really fast and efficient. And now I will try to jump a little. The major let me, that's okay. The major question that I've left unsolved so far is how do you handle noise and how do you choose your nonlinear operators? So those W's, which essentially they are if they are constructed smart enough, then you have a solution. If they are constructed in a naive way, nothing will work. So these are images from a recent paper published in the summer. What happens if you take a naive choice of those W functions and you try to repeat the same idea that I've just mentioned to create dense registration? This is roughly what you get. So it sometimes works, sometimes it doesn't, and or it works not good enough. And what we used here in this example, the set of W functions that we have chosen are the set of characteristic functions, namely each W, so that you will get also, I'm showing it so that you'll get a feeling for what the W's are. Each W, if you choose the W's to be the characteristic functions, if you have an image with 256 gray levels, W1 will be 1 on intensity level number 1 and 0 elsewhere. So essentially, if you take this approach of it's like the Lebesgue integration idea or level sets idea, where essentially W1 is 1 for pixels that are at gray level 1. W2 is 1 for pixels that are at gray level 2. And essentially, what you do is you evaluate the 0 and first order moments of these binary images, and you do it for all levels. Mathematically, it makes a lot of sense because if your image is anyway quantized, any W function can be represented as any W function can be represented as a linear combination of the characteristic functions, because this is all the information you get. You've got 200, the images are quantized in 256 levels. So the next question was, okay, if we are in a quantized world, and so we might as well start with characteristic functions as our first choice for the W functions or for constructing this nonlinear operator. How do we optimize it? And in the paper, there is a construction using SVD. Essentially, it boils down that when you improve it, when you don't take a brute force approach and try to optimize it, you get much better matching. Essentially, what happens here with this choice of the W functions is that since there is noise in the observations, essentially you keep only those W functions that are relevant to the signal, and you throw away those W functions that confuse you because they're related to the lowest singular values, which are mainly due to the noise. And finally, I'd like to show you some examples of what we do with the same idea in 3D. Okay, this is from last month's ICCV. the ideas I presented here work regardless of the dimension of the data. So there's nothing holy in 2D or in 3D or in ND. You just have to understand what are the basic properties of the operator and adapt them accordingly. So in here, we used the same mathematical framework in order to solve the problem of registration of 3D point clouds, where again, in 3D point clouds, I just have to mention, are different from images in the sense that images are very regularly sampled. When you have a point cloud, there is no grid, sampling is non-uniform, noisy, and essentially there is no order in the sampling, unlike what happens in 2D. So what we did in this work is essentially to, using the same principles of the universal manifold embedding, take tentative key points and define balls around them, and evaluate and define these balls around the putative key points as your object, evaluate, characterize them using those UME matrices, and then if you have 2 points that you think that they match, evaluate the distance between the subspaces that are evaluated from the neighborhoods of these points. And if they indeed match, you should be getting zero distance. And this seems to work very well for solving the problem of outlier removal when you try to find correspondences, again, in order to estimate the transformation between the objects. This is a scheme of how it works. So for each object, we find a set of putative key points, and then we try to evaluate the distance between these not these key points, but the neighborhoods of these key points. And the way we evaluate the distance is not Euclidean, but rather we evaluate the distance between the subspaces that are spanned by by the T operator, and we finally obtain a procedure that allows us to very accurately handle very difficult cases where outlier rates are above 99%. And the key here is that using this operator, once we solve the problem, or like every step of solving the problem, we get both an estimate of the distance between the subspace and the transformation that relates them. Now, if you have a rigid object that undergoes some rigid transformation, if correspondences are correct, the transformation between two key points should be the same as the transformation between any other two key points, because it is the same rigid object, and it should be exactly the same as the global transformation. Now, if you have outliers problems, which is the case we're dealing with here, then you will have a cluster of correct samples, where correct, I mean the distances between the subspaces will be zero, and the estimated transformation between the subspaces will be clustered in a narrow cluster, where around them you will get large numbers of different estimated transformations that simply result from the fact that you tried to match something to something which doesn't match it, and therefore you get an arbitrary random transformation. So by using this dual consensus idea where you say these 2 points indeed match if the transformation is in consensus with other transformations and the distance between the subspaces is close to 0, then you can handle very, very difficult situations that other methods fail to handle. You can see here is the cluster of where the correct matches are concentrated, and the outliers are simply scattered randomly around in space. I think I'll stop. This is how the operator looks like in 3D. Okay, I think I'll stop here. Questions? Everything is well understood, or nothing is or nothing is understood. That's true. Okay, then you go.
Thanks for the presentation. In fact, you mentioned the fact that you use an extrinsic.
They use what?
An extrinsic measure. You use a Fourier's norm.
Mm-hmm.
It's an extrinsic measure. It's not an intrinsic.
It's a Frobenius norm. Here, this is what we use.
Or if you want to associate it to the Grassmann manifold, you have a closed form for distance.
I agree. You don't have, for the intrinsic distance, you don't have a closed form. This is why we don't use it.
Okay.
We use the extrinsic distance, which is essentially an approximation where instead of going on the manifold, you allow the distances to be calculated not on the manifold itself, but rather, like if you think about a circle, the geodesic is computed on the circle, but the extrinsic distance allows you to measure distances between points by evaluating, I don't remember the word in English, this length, instead of going that way. But if the distances are small, then no problem, and it allows you to.
Because in fact, you have different choice in terms of.
Pardon?
You can select different.
There are many ways. There are many distance measures on the Grassmann, but this one is simply very intuitive and very easy to compute. And if in case you are right, and the subspaces do really present the same object, you expect this distance to be small. So the only question that is really relevant here is it 0 or bigger than 0? If it's bigger than 0, I don't care. It's wrong.
And if you consider something different than the affine transformation, you lost the linear.
Okay. We had in the past work where we showed results. It was published as far as I remember in the information theory transactions we considered time warping or elastic transformations on R1. The problem is that if you consider elastic transformations in higher dimensions than 1, then there is a problem in the fundamental solution, because the Jacobian of the transformation is now a function of the coordinates, and you cannot separate the solution into two steps. So for the time being, in order to avoid this mathematical difficulty, what we do is that we as I explained in one of the slides, we take the approach of piecewise approximating any nonlinear function by a piecewise linear approximation, and this is the idea of the tessellation. Now, remember, you're dealing not just with the geometry that is being transformed, but also with the radiometry. So there is the solution. The solution for which works by tessellating the observation into triangles or any tessellation that you'd like makes sense physically, because then both the geometry, if you look at small areas, the geometric transformation can be linearly approximated, and furthermore, you don't expect the radiometry transformation to be more complicated than monotonic if you look at a small enough area. So you catch two birds with one shot. That's the idea.
I have a question, but I don't come from the image processing background, maybe, but so basically, how well does this method work for more abstract representations? So, because in the examples you showed, so we are trying to match the same object, maybe, but because the set of the manifold of the
Appearances.
realization is well enough, but if we go to a more abstract representation, so I want to detect not this specific object, but a set of similar objects. So not only this car, but the set of, let's say, red cars in general. So the manifold of possible realization is bigger.
Okay, I think I understood the question, and this is why, or I hope I understood the question correctly. It's, look, what I presented in the first part of the talk was the fundamental idea where you can assume that you have a single object, it is isolated, and what you observe is different transformations of that object. Now, if you have is not more complex than affine, and radiometry is not more complex than monotonic, because otherwise, if this assumption is wrong, you would have split the triangle into smaller triangles. But at the end of the day, if you look at the transformation in the radiometry can happen. And essentially, we rely on this assumption in the sense that if you use some key point detector in order to create the initial tessellation, if there are radiometry changes, it will pick a point. If there is some geometric transformation, there will be some discontinuity and it will pick it up.
Thank you.
Thank you.
Thank you very much.